welcome to the third day of the Replication Across the Sciences Conference. It's my pleasure this morning to introduce Richard Shiffrin from Indiana University, who will be talking to us about the practice of science, aim for progress, not reproducibility. Please join me in welcoming.
Thank you. I'm pleased to be here. A very interesting conference so far. I think it's important for me to see that at least you take something of value from today's talk. So I'll start with something important, and then it'll go downhill from there.
May I just ask if you...
So I want to invite you all to consider coming to the annual conference. Some of you already have heard about this, that I run every summer. This year it'll be in Austria, Seefeld, Austria, June 17 to 22. It's a open invitation conference. Anybody can come. And the day, 6 days, it's generally organized around cognitive science. Oh, there's a problem with the mic.
There is. So would you mind? Could you
Yeah,
speak up a
so
little
let
more?
me try to shout. This conference is open. It's 17 to 22 in June. And the days are free every day from morning to 4 in the afternoon, talks from 4 to 8, and then dinner. And it's an annual conference, and this year it's in Austria, and you can look it up on the web under ASIC for Annual Summer Interdisciplinary Conference. So that's the important part. Now we'll turn to reproducibility. Now, please interrupt and ask questions. So I don't like to just talk. I mean, I like to talk, but not just talk. So since I may not be speaking loud enough, the text is on the slides. So I'll just start with some bullet points that I'm going to try to cover. The primary goal of science should be progress, not reproducibility, not validity, not rigor, and not obeying simple rules. I think progress is presently going forward at far too rapid a rate in all fields for anyone to follow, except perhaps in their own narrow fields. I think optimal progress requires a healthy dose of irreproducibility. An important point in my mind is that this cottage industry derived from the reproducibility crisis harms the public perception of science, and even, in some cases, scientists' own views of their own fields. And related to that, even though all fields publish irreproducible findings, some are chosen for unfair criticisms. Then I think that one-size-fits-all prescriptions to solve problems of reproducibility are generally a bad idea and will hinder progress. And of course, this crisis, as it's so called, is not new. It is not a crisis. Science has operated this way since it started. And these are some of the main points I'm going to try to cover. I don't think the time I have to speak will give time to elaborate these issues in detail and others. But I'll start with some of the most important issues and keep going until time runs out. And please interrupt and complain as I go. So, I think that the harm that's caused by all these discussions of reproducibility needs a remedy, and it's simple. We should focus on the best of science, not the worst of science. And right now things are out of balance because most of the people who are dealing with reproducibility are focusing on things that are wrong with science and usually picking examples of bad science when we should be focusing on the best of science because science is going forward in amazing ways in every field. Gosh, I hope I can speak up. I'm not in favor of bad science. No one should defend fraud. We shouldn't defend publications that produce significant harm, like claims that vaccinations cause autism. But most bad science publications do little harm. There's an enormous number of publications that somehow make it through the reviewing process, and they are some or all of flawed, pedestrian, uninformative, uninteresting, and not harmful. And these would not slow scientific progress if they were deleted, but they also don't slow progress by their publication. And why? Well, the number that don't harm science, that are not really very good, very likely total more than 500,000 of the million-plus publications every year. Why? Because 500,000 publications every year are never cited even by their authors. One might nevertheless want to suppress these publications, but any methods I can think of to do so would slow scientific progress by adding burdens to good scientists and slowing or stopping publications that will lead to progress and possibly even breakthroughs. You could demand for a publication that the results be based on very large amounts of data with very large power, based on several studies representing variations of the experimental paradigm and carried out by several independent groups at different sites with different beliefs. Well, results surviving this gauntlet would very likely be reproducible. However, most results wouldn't survive, and this procedure would eliminate many valuable studies and would slow scientific progress to a crawl. Well, it seems obvious that progress is not slowed and harm is not done by articles that aren't cited. So the benefit of adding burdensome regulations to stop them would not justify the cost. What about the publications that are cited, largely because they show promise, but they're not valid? Well, because these are thought to be important, they are pursued in further research. Some of these don't pan out, and they're not pursued further. Some are valid and lead to important advances in theory and application. Some are invalid, but sometimes the research that shows that they're invalid is valuable and leads to further important breakthroughs. That's just the way science works, and it's the way progress takes place. So that's the normal way that science operates. There are, of course, scientific gains that accrue when science lets many publication flowers bloom, some worthwhile and some that are not. Science generally operates in an infinitely complex universe. At least most of us think so, except a few odd physicists. With scientists fumbling their way forward using trial and error and guesswork based on noisy data, non-optimal experimental designs, and erratic implementation. Thus, the scientific method is obviously imperfect, and it must produce many findings that don't bear out and don't prove useful. Despite that, amazing progress has occurred, and the benefits operate all aspects of modern society. Bottom line, we must accept a good deal of irreproducibility as part of the optimal practice of science. Do publications of these promising but invalid papers harm science? Well, yes, if scientists are stupid and believe everything they read. Scientists aren't stupid, they are skeptical. We all know that many reports are invalid, and we treat reports as pointers toward possible progress, toward possible further investigations. The idea that we should accept every publication as valid is absurd. So I'm arguing for the necessity of publishing many results and inferences from those results that are invalid, in part or in whole. But these kinds of arguments place the focus on replication, and in particular upon replication failures. And unfortunately, that puts attention on the worst of science and failures of science. And this very discussion contributes to the harm done to the perception of science by the public and by scientists, for that matter. So this focus that we have on replication, which is sort of involves self-criticism, has cast science in a light that is way out of balance. So there's a fairly substantial number of mostly well-meaning scientists who are engaging in a process of flagellation of the scientific progress, of the process, based on analyses of mostly bad and pedestrian scientific publications. The problem is not replication, but the fact that we are evaluating science on the basis of what we do poorly. So scientists need to place the focus on the best of science, not the worst, at least balance these current discussions with a focus on what we do well. And by the way, I said this yesterday, but I'll repeat it. This is a little bit outside the main theme, but it has sort of something we covered in our PNAS article last year. How is rapid progress possible, given these various problems that are facing scientists, problems of irreproducibility and many other challenges to science? Challenges like limited time, limited resources, including financial ones, overwork, responsibilities besides research, a flood of publications beyond anyone's ability to process them or read them, inadequate reviewing of submissions and grant proposals, the basic difficulty of scientific discovery in a chaotic universe. So scientists surmount these challenges as best they can with their dedication to pursue truth and knowledge, but that's not enough. I think that the ability to overcome many of these difficulties lies in the scientific social networks that occur in discussions at meetings like these, colloquia, workshops, and other venues, and is due to the research and collaborations that emerge from such discussions. But that's a different talk, a subject for a different talk at a somewhat different conference. So to return to the main theme, the result of the recent preoccupation with bad science has been to harm the public perception of science, to place the funding of science in danger, to add new one-size-fits-all rules about how one should practice science, rules that add to the burden of experimentation and publication, and has even led scientists in some fields to doubt the value of research in those fields, including some of my own fields. This is basically an absurd state of affairs because science is progressing so fast. So the public can't keep track of the flood of exciting developments. Occasionally there are news reports about one or two reports in particular fields, but even scientists can't keep up, except in our own narrow domains of expertise. Well, basically, how we evaluate the current state of science depends on where we look. If we look at what's good or what's bad, yeah.
How do you think of the contrast between what's good and what's bad? So would you say if we look back 10 years ago at the papers that have been most cited, we would define the papers that have that kind of track record as the best, or just sort of operational?
Yeah, it's hard. Basically, the ability, the ability to decide what's good is a matter of scientific judgment, and it's a hard process. It's hard. That's that's just as hard as doing science, is trying to decide what's good and what's bad, and we do that whenever we review a paper, whenever we read an article. This is a matter of scientific judgment, and that's how we do it. It's difficult to do. This has been true of science since the beginning, and citations aren't a particularly good way of judging quality of papers. They happen somewhat accidentally.
But that must mean that you apply some evaluative criteria, and I guess one question would be, are those evaluative criteria coming from what you take to be good science, and would there be a sense in which, in focusing on good science, we can arrive at rules that would be useful for the future, or no, we just look back and we say this is good, this is bad, and there is no metric or no guidelines that might make things.
Yeah, it would be wonderful if we had a metric that would define what good science is. The advantage of that would be that we could build a computer program that would do science for us, and we could eliminate scientists if we had such metrics and such rules. Unfortunately, that's the problem, is that science is a very messy process. It requires a lot of creativity and a lot of judgment. And we can't seem to make rules that allow us to define what's good and what's bad. We know it when we see it. And somehow or other, we know that it works because science keeps progressing. But I haven't found any way to define metrics that define what good is.
So you can't make it explicit what good is, you just sort of ostensibly...
Well, there's some things that on average, good publications on average are better. The kinds of publications that I've become known for are ones, for example, where I carried out various experimental manipulations, many different ones, where I try to pursue given theoretical models or proposals in different domains in different ways, put together a lot of studies that converge on the same theoretical ideas, and then publish them as a large group, and that together they make a persuasive case, and combine that with some mathematical modeling and formal modeling. And this is one way forward. That's the way I've done it. That seems to work well for me. If you instead talk about publications where somebody carries out a simple experiment to see whether a mean is greater than 0, you're not going to learn too much. I think that's less effective as a way of doing good research, but it's common. Most of the discussions of reproducibility, and I'll mention this later, have to do with very simple experiments and binary questions. Is something greater than 0 or less than 0? Or does something exist or not? That kind of question. Much of science doesn't operate that way. Much of science operates by looking at a pattern of results over a wide variety of conditions with a set of different measures. And when they converge, that gives us a sense that we're on the right track. And so these are qualitative issues. It's hard to put them. It's hard to make metrics for them because it comes down to a matter of scientific judgment. But we know it works. Somehow or other, it works.
I asked a question not because I doubted that there was a sense of scientific judgment that would be involved in discriminating good for bad, but if we're going to make the claim not just about fields where each of us has some expertise in order to make that judgment call, but trying to look overall, then you're making a claim that there's good science is doing well and bad science is affected by
definition.
Well, that could be just tautologous, or if you had a different way of defining the contrast, then you could try to assess what part of the literature is it that is having these problems and what are the characteristics of that. And that's why I was asking if you have
I think that there's several different aspects to that question. I'll try to deal with some of them in the talk.
You suggested one, which is the kinds of questions that people were pursuing were simple yes or no questions, or those were the ones where you see.
I think sometimes, this is again a matter of judgment, sometimes the yes or no question can be very important to answer a theoretical issue or problem. Occasionally, yes or no, research aimed at a yes or no question is critical. If you, for example, check Einsteinian predictions about light bending around the sun, that's that's a sort of yes or no kind of experiment and question, but you don't think so. All right. In any event, there are examples where one can carry out a simple experiment aimed at a yes or no question, and it can be valuable. In many domains and many times, you want to collect a large amount of evidence over a large number of different domains. And I'll be talking a lot about generalization and the fact that we generally don't want to have a result that holds only in one specific context, at one specific time, in one specific place. We want things to be robust and generalized across many different situations. So, okay, so I'll be covering some of this if I have time as I go forward. So, okay, I say we need a much greater focus on the best of science in order to produce balance in this discussion. But of course, in recent years, we've seen a focus on these problems of scientific practice. And then that has led to a variety of proposals that are claimed to solve these problems. And I'll discuss some of these because I have to. And some solutions are, I think easily worthwhile when appropriately applied. So generally, open science and full reporting is a good idea. That's important in science that we explain what we did and what was found and let other people check it. and that applies in almost every domain, but there are still fuzzy edges to that claim, as I'll cover. We, of course, want to stop justifying bad publications with bad statistics. There's all kinds of issues having to do with the justification for publication using silly statistical rules to do so and misapplying statistics. And journal reform, I think, is important. We've already had some talks talking about this. We should change journal editing and reviewer practice to foster publication of, for example, fostering publication of scientifically sound, contrary findings, opinions, and conclusions. Right now, there's as people pointed out many times, there is a tendency to suppress any findings that don't replicate or don't reproduce earlier findings or claims. Well, it's natural for this to happen. Usually the contrary articles are sent to the original authors. And naturally, the original authors tend to say this shouldn't be published. And this is not a good idea. And I'll say something more about that later. Of course, if we do foster the publication of contrary findings, that's great. That reflects the uncertain nature of scientific findings and conclusions and helps produce scientific self-correction when needed. Well, let me say something about that, because I had some experience that when I was an editor, and have similar experience when I'm doing editing since. I adopted a policy that I always sent to submission, the correction, let's say, the one that was contrary to some earlier publication, to the original authors for review. But I let everybody know that I wouldn't use the evaluation for publication that those authors provided, because I could pretty much assume that they would say, don't publish. And I made that decision about whether it was valuable to publish, and I let the original authors and everybody involved know that that was the case. And so I ignored any recommendation concerning publication from the original authors, but I assumed they would give the paper the most careful scrutiny possible. They would be concerned to look for errors, so I used the content of their reviews, but not their evaluation. And then based a decision about rejection or revision or publication based on my reading, and if there were any neutral other reviewers, those would be the decision about what to do with the paper would be based on that, not on the evaluations of the authors. That's one way to improve editorial practice. Now, I think that many proposals that have been put forward to deal with irreproducibility may slow progress. And some of the so-called solutions are statistical in nature, and that makes sense in a way. Bad statistical practice is indeed used to justify publication of some bad science, like p-hacking or many other statistical misuses. A number of the statistical remedies aren't needed and aren't helpful. Sometimes they substitute universal rules for scientific judgment, partly because they are too simplistic, some of the suggestions, partly because they're too restrictive, that slow and prevent reports of new and important results, and partly because they repeat old problems in a new guise, such as changing null hypothesis testing criteria from 0.05 to 0.005 when null hypothesis testing is sort of ridiculous in the first place. And it's still bad even if you use 0.005 instead of 0.05, and there's a long story behind that. So in general, statistics should serve science rather than science serving statistics. Some people have argued for exact replications, that we should shift toward exact replications in place of conceptual replications. There was one of a number of examples was an editorial by a recent president of the Association for Psychological Science. I think this is backwards, completely backwards. Conceptual replications, as they're usually defined, produce generalizations and show robustness. They're the way that science has always operated and should operate. When we see a result, whether or not, even if we don't believe it, we usually carry out an experiment better. We don't try to replicate it. There was yeah.
What is a conceptual replication?
Well, that's defined differently by different people, but generally I think of it as an attempt to refine, extend, and elaborate the concepts, results, and/or conclusions and theories that are proposed in the original article, where you extend the ideas beyond the original notion. So rather than just try to say that this particular result holds if you do it exactly as best as possible in the original setting with the exact same procedure, you try to find out more about it. When does it hold? When does the result hold? When does it not hold? What is the theory that accounts for it, and how do we test it in a different way, and so on. These are the kinds of things that usually go on. So most scientists have done that. They don't take the original result and try to replicate it, but they try to refine and extend it. And that's the right way you do it.
Of course, I don't disagree with that, but that kind of presumes that there's some truthiness to the original finding. To say when does it hold, that might not exist. It might not hold.
Well, there's two kinds of errors. I'll cover this later. There's sort of qualitative errors where, for example, where, for example, a result might be in the wrong direction of that reported. But pretty much any, excuse me, pretty much any variable we manipulate in a real setting in the world has some effect. It's not zero. I don't know of any real effects that ever are zero. It's a question of whether they're big enough to matter, whether they're important. Some effects are tiny, but are important. Some effects are large and unimportant. This, again, comes down to a matter of scientific judgment. And there are errors that do point in the wrong direction. And those would be invalid. And it's important to identify when that happens, because clearly there are errors involved in the process. But much of the problems we see in terms of reproducibility and so on aren't of that nature. It's a question of whether the results reported are big enough to matter. And those are, I'll cover this more later about utility and when we should be pursuing earlier results. But that's part of the nature of the scientific process. Is, you know, did you want to?
I did, because I mean, it seems like maybe this would apply in some areas of science and not in all areas.
Yeah.
Right?
Which area wouldn't apply?
Well, I think the area of science that I work in, because you're trying to run intervention experiments and you need to have some degree of stability with respect to the phenomena that you'd like to discover the mechanisms of, you need to have the replication of the cognitive phenomenon you're interested in, so that then you can manipulate and determine what the mechanisms are across different experiments, right? So.
No, I disagree. You're talking about, say, neuroscience.
Yeah.
No, it's almost impossible to do a replication in any real sense. It'll be different people, and the people are different, vastly different.
That's
the
true, but that's
design is different, the brains are different,
right,
the
sure,
measuring
so
apparatus is different.
We can talk about a replication continuum, but you try to get some sort of stability by means of using the same procedures that another group has
Sometimes you do want to use the same procedures, and sometimes you want to use a converging evidence from a different procedure. So maybe you want to use fMRI and you have converging evidence from PET scanning or something. You know, this is all a matter of good science.
I'm not saying that they're not. I just think they're both involved, if anything. I don't think one is better than the other.
What I'm saying is exact
replication. Kind of question you're trying to answer.
I'm saying that exact replication is impossible, number one,
okay.
and that we are always doing some kind of conceptual replication. But it's a matter of degree. Sometimes we're closer to the original paradigm, not exact, closer. And sometimes we're doing, you know, sort of extended variations and so on, searching for converging evidence about the processes that are involved. And that occurs in neuroscience and occurs everywhere, in every area of science. So as I said before, most of what I've done in terms of conception is what I could call conceptual replications, what I'm known for. in areas like memory modeling, attention and automaticity, priming, and so on, and cognition. What I've usually done is carry out a wide variety of conceptual replications and demonstrating core concepts that operate across a variety of tasks. And then the way I do it, I usually connect these tasks and concepts with formal mathematical and computational modeling. But many others make major contributions with conceptual replications, but not with formal modeling, but based on less formal and more conceptual hypothesis formation and hypothesis testing. Either is fine. I happen to prefer doing mathematical modeling. Others do it less formally. But the idea of carrying out a large of conceptual replications, especially in areas that are very chaotic, like psychology, is a good one and is a good way to carry out science, but I think this applies everywhere. We want results that generalize and are robust, and we don't usually like results, very seldom, that only occur in one exact setting. That wouldn't be usually of much scientific interest. So replication is not a particularly good idea if you define it narrowly. Because, you know, who cares if something only applies in somebody's lab, in somebody's setting at a certain time of day, you know, and so on and so on. That's not of great interest. The attempts at exact replications that have been carried out by a variety of investigators have been problematic in various ways. Sometimes there's been attacks on reported results and defenses of them that tend to be misguided in my view. I don't think attacks on a reported result should stop with the demonstration that a replication fails and then conclude the result is wrong and the research is flawed. That's sort of a minimalist kind of approach and is pretty useless. Research that follows up earlier research should seek to find the conditions in which the result does and does not generalize, and what are the implications of those findings. And when you defend an attack, if say the original authors do, on an original report, you shouldn't be satisfied in saying, well, there's some difference in the way they did the replication, some minor difference that's critical. That may be true, but again, that's not much of a defense and it's not much help for scientific progress. Instead, you should, when defending an attack, search out and discover the conditions in which the original results do hold and what are the implications of the conditions in which a result does and does not hold. I'm trying to move away from an all or none treatment of results as if things either exist or don't exist to a more sensible, continuous view of the size of results and the importance of results, rather than an all or none view that something satisfies some statistical criterion and therefore is real. And of course, as one of you already pointed out, there are results that are simply wrong. They go in the wrong direction, rather than, say, dependent on context. And of course, there are many ways you can be wrong. Errors in design, errors in programming and analysis, errors due to experiment or bias and fraud, and so on. And such factors can cause qualitative failures, such as results reported to go in the wrong direction from what they really should be. But many results don't replicate because they're wrong in a different way. As I pointed out, they're maybe too small to measure with the tools at hand. They may be small and of low statistical power, but nonetheless important. They may be based on reliable data, but interpreted incorrectly. There's many different ways it can be wrong. And with respect to some of these latter sorts of irreproducibility, I want to repeat that there's no experimental manipulation that has a truly zero effect. Coin flips do not produce heads with probability of 0.5. They can't. Coins are asymmetrical. Now, some effects are too small to be important. Perhaps the difference between 0.5 and the true probability of heads is 0.00001 or some number. But some effects are small but important. informing Facebook users that their friends have voted may produce a minuscule increase in the user's probability of voting. But when this occurs for millions of potential voters, the effect can swing an election. So what's important is not simply dependent on size of effect, but importance should be put into place. So reported results have to be judged, not on the basis of replicability, or not solely so, but on potential importance, potential utility, importance for pointing out worthwhile directions for further research. I've made many decisions on this basis in my own long history of editing. I remember, just to take one example of many, Anders Ericsson tried to publish. I was editing acting as a reviewer for an article sent to Psych Review, one of our leading journals in the field, using examples of musicians and training to argue that anyone could become expert, completely expert in anything, on the basis of enough training and enough hours a day training the right way. Any one of us could become expert in absolutely anything. The only thing he produced an exception for was height. He said you couldn't train height. But everything else you could train if you did it right and long enough. And this was a flawed research. It was correlation research based on observations of musicians training a long time and becoming good. It was obviously flawed in terms of correlational research that didn't have a causal basis. It wasn't an intervention, and other reviewers were very negative. And I argued this was worth publishing because it was important and useful to follow up in further research, because there was this idea that you were born with the ability to be good at things. And this was taking the opposite view, saying you could train to be good at anything, and it was an important message to get out there. Maybe it's right, maybe it's wrong. Well, it's neither right nor wrong, it's a matter of degree. But the question is, it's a different view that would change the way society operates. So it was important to get out there, and I convinced the editor that this was worth publishing, flawed or not. Utility and importance is something to be taken into account, not replicability, necessarily. So, many results are worth reporting then, that even if there's a reasonable probability the replication will fail. Now, of course, another set of reasons for this is that the costs and difficulty of research are sometimes so high that sometimes it's best to report potentially important results before you can assure validity. I probably will get an objection to this from physicists in the audience, but examples would be like neutrino research in physics, where it's difficult to do the research, expensive and slow, and occasionally you get a neutrino capture every few years or what have you. This is not a easy subject to carry out research in. And there's many examples where the costs and difficulty of research means that you really can't afford to wait forever to get enough data to be sure of your validity, and you should report potentially important results to let others pursue it in other ways. And again, this may or may not be true, but the example that I like to use is that the gravitational wave research had a famous report by Weber in the 70s claiming detection of gravitational waves using equipment that was not sufficiently precise to actually make the case, as it was discovered shortly after. But my view is that the demonstrations that you needed greater precision that came out of that failed report eventually led, or helped lead, to the successful LIGO demonstrations many, many years later, when the sufficient precision in the measuring instruments was finally managed. This is sort of one example of many where failures or irreproducible results can lead to progress down the road as the research is pursued. Pre-registration. pre-analysis, as it was also described. So I think it's mostly, I don't have any objection to anybody pre-registering if they feel like it. But I think I would hate to see a rule that we had to carry out pre-registration to publish. And there's many reasons why. And the first is what I see is that scientists aren't omniscient. And they usually can't design studies that are perfect in advance. That's why we have trial and error in science. Science is basically a post hoc method driven by what we discover and what we find. In fact, we seek to discover new things and new concepts. Pre-registration is designed to discover what we already know and expect. It's been argued that pre-registration facilitates publication of failures to replicate. That is, if we pre-register a study, then we're allowed to publish it. Well, I think that's better handled by changes in journal practice, where the journals agree that it's better, or that we should foster publication of results contrary to earlier ones. Others argue that pre-registration makes the scientists think more carefully about their planned study. Well, good scientists tend to do this. I like to think that we do think carefully about what we're going to do, but of course we're not perfect at it. Usually I go through 6 or 7 iterations of an experiment before settling on the final design that seems to work well. So the idea that you're going to turn bad scientists into good ones by making them pre-register is sort of a silly idea. And of course, any pre-registration system can be gained. You can pre-register a study that you've already done. We do that with grant applications quite often. Propose studies that you've already carried out. Good way to get grants. Adversarial studies are interesting. I like the idea. Researchers with opposing views, theories, or results plan all aspects of a critical study together, agreeing to live with and publish the results, whatever is the outcome. Okay, that's a step up from pre-registration in a way, because at least it enforces highly motivated thinking and planning in advance. It nonetheless suffers from the same problems. So one of my postdocs carried out such a adversarial study. It was E.J. Wagenmacher's. He had picked on a set of 20 studies, all showing that flicking your eyes back and forth, right and left for 20 seconds pretty much makes you better at everything. There were a whole set of things that was supposed to make you better at. They were even using this to treat PTSD. So imagine looking straight ahead, looking left, looking right, looking left, looking right. Do that for 20 seconds. It was supposed to make you better. It was like 20 studies showing this. E.J. thought this was unlikely. They planned he took the main author who was involved in these set of studies, there were a number, and they planned an adversarial study to check this. They agreed on everything. They agreed on, eventually, they agreed on the design. They agreed on the analysis, on the statistics, on everything involved in the study. And then they carried out the study in 2 labs, each of their labs, according to the design that they agreed on. Well, what happened? The results showed that that eye flicking hurt you rather than helped you. So you think that would end it? Well, the author that lost the adversarial study then thought of about 10 more things that they should have done once he saw the results that weren't in the critically designed study. Because once he saw the results, he thought of new things. Well, of course, maybe he's right. You know, one scientist is not omniscient when they're designing study, but 2 aren't omniscient either. Once you see the results, you think more deeply about what's going on. Maybe there are things you missed.
Can you just define briefly what you mean by pre-registration? I think I know what you mean, but
Well, there's about 10 different ways to pre-register. And so I don't, I'm not referring necessarily to any particular one. There are a number of journals that are saying you have to pre-register a study in order to publish. That's going pretty far. There are different varieties of pre-registration, so I'm not sure which one you're thinking of, but There is, you know, how you would judge them may depend on which variety you're talking about. I don't have any objection to optional pre-registration, where if you feel like doing it, you can do so. It's good for historians of science, so you get to see if it's done well, and you're not sort of making up the pre-registration after the fact. Is an interesting equivalent of lab notebooks, where you can sort of trace the thinking of the investigators. So that might be useful for historians of science. Anyway.
I was going to say one working definition of it is just stating in advance what you plan to do before you do it in a way that's publicly verifiable by others. And that's kind of an umbrella term.
That's one of many variants. Stating in, as I say, what I think of is that stating in advance what you're thinking of doing is good for historians of science. It sort of tells you one step along the way. Of course, in the way actually science works, there may be 6 or 7 versions of that as you move forward doing your experimentation and as you discover things that you need to do better. And I'm going to talk about optimal stopping in a little bit, which is relevant to this, which has to do with the fact that there's an iterated series of steps involved in real science. So it's not as if you're planning in advance one thing. You usually plan many things and take successive steps before you eventually settle on something that works. Okay, there's a number of statistical and methodological issues that play into these discussions. As I said before, discussions of reproducibility refer to reproducing a single effect, usually. Refer to reproducing a single effect or single dimensional data statistic, things like a mean, an interaction, or a trend. And studies reporting such simple statistics can be useful, but I don't think are the best way to foster scientific progress. We learn much more when we study multiple conditions and establish an overall pattern, even when each condition would be viewed as underpowered, considered alone. It's a pattern. What we're interested in is a pattern of results over a wide variety of conditions with a wide variety of measures. And that's usually the way we learn more. Those of us who build models to understand the processes at work almost always never model one effect for obvious reasons. It's too easy to find models that explain a single finding. But rather we build a model to explain a system of findings across a variety of conditions. And of course, you can do this kind of research using verifying your results and claims over a wide variety of conditions, whether or not you carry out formal modeling. That's just the way I like to do it. Now, there are many factors involved in good scientific practice that cause statistically non-reproducible results. Now, I want to mention this because it's important. Consider factors that produce a kind of regression toward the mean. The tendency for a second study to show smaller effects than the first. Much of science is exploratory, and scientists usually carry out several versions of their studies, refining the design and conditions, adding or changing control conditions, and choosing design parameters that highlight most clearly the results of interest. These alterations are often based on examination of the preliminary results, results that help eliminate mistakes and help gain insights into doing the experiment better. This process of refinement continues until some optimum is reached. The early studies in this process are often useless, especially if they're based on errors. And of course, those shouldn't be published. Thus, scientists wait until they get things right. They publish when they think the results are clear and make a persuasive case because they've got things correct. They've got things designed right. You can't keep going forever doing this. You can't wait until everything's perfect because nothing is perfect anyway. The scientists must choose when to stop and when to publish. And the stopping point is obviously going to be when the results look good and the implications look clear. And using this stopping rule will cause the reported results to be accidentally better than they would have been in an average version of the same study. This produces a statistical bias. Thus, an attempt at an exact replication will almost always show a smaller effect. Of course, in addition, stopping when the design most clearly demonstrates the desired results means that the study is well tuned to the local context. The design is tuned to the local environment. A new study will always be in a new context, so the previous tuning will no longer be optimal. And again, you can expect a smaller effect. You know, we can't expect, or we expect a certain lack of generalization if we start changing the context in which we do studies. So an appropriate scientific stopping rule, which is the right way to do science, takes advantage of both statistical noise and design optimization. And as a result, the effect size will be less on average in subsequent studies. Thus, when we see what appears to be a failure to reproduce, the smaller effect size could just be a normal part of the scientific process, not necessarily a sign of bad practice. And there's been a number of large-scale replication studies that you hear reported in the news, reporting that only 50% or 70% or what have you, whatever the number is, of studies replicate. But it depends how you define replication. We expect the results to be smaller when we try to replicate. So we can't just interpret them by some binary count of number of effects that are as large as they were earlier and so on. I think some of the debates about the meanings of these replication studies depend on this misunderstanding of the nature of replication. The difficulty of collecting evidence often forces publication of underpowered results, of course. Many cases involve health publications. Investigation of a given disease syndrome may have highly limited access to patients. One would never want to argue that the diseases should not be studied because the patients are hard to obtain. One would never want to argue that the findings should be suppressed because the power is low if you can't get more patients with that disease. That would be unethical. And it certainly would prevent progress in dealing with the disease. So that's just one example. There's a wide range of situations in every domain of science where enough data can be difficult to obtain. Okay, and of course, this is common for many reasons, including cost and money and time. All research requires monetary resources, some extremely large. That's found in every field of science. Astronomy, physics, chemistry, biology, computer science, through the social sciences and the health sciences. Another cost is time. If data can only be collected slowly, someone already mentioned during the conference, an astronomer may not want to wait for the next supernova. Balance is needed, the amount of data versus the cost of research. And I don't think it would be a good idea to prevent publication of promising research that's based on less than an ideal amount of data when the cost of research or other factors limit the ability to collect more. That would obviously slow progress. So when more data is difficult to obtain, it can make sense to publish promising results. Maybe that will spawn new research ideas to investigate the phenomena in other ways that are less costly and can be carried out. Okay, if one desires high power, what should the criterion be? And I prefer a Bayesian utilitarian approach, stopping data collection when an amount of evidence is reached that determines the effect size to a level of accuracy that allows one to draw meaningful conclusions. Sometimes the meaningful conclusion will be the existence of an effect whose size is large enough to matter. Sometimes the conclusion will be that the result is extremely small or too small to matter. The criterion amount of evidence likely ought to differ by field and context of the study, and this requires good judgment, not just a simple rule or criterion. Because they are subjective, and there are differences among researchers in how to quantify them, two factors tend not to be incorporated in statistical inference: importance and experimenter bias. Now, other subjective factors are common in Bayesian inference. Prior knowledge about hypotheses are built into Bayesian inference. Prior knowledge about data is also easy to introduce into Bayesian inference. So I don't think there should be any objection to incorporating subjective judgments of importance and bias, and we need to do it. And scientists do it implicitly. So utility is easy. If you have some hypothesis, Hj, it has importance Ij, and has posterior probability Pj, just the product of those two would be the posterior importance of that hypothesis. It's easy to introduce utility in that way.
So importance is just a measure of significance of the result?
Well, this is again a matter of judgment. Sometimes importance is significance for society or for health. Sometimes important is for theoretical advance or for understanding. This is again a subjective judgment. But however we define it, it's up to the scientists to know what they think of as important. It's not easy. This is difficult. Science, doing good science is as much an art as it is a science.
This is just a basic expected value.
Yeah, no, I was just wondering if it was a technical term.
But how you define importance is going to be up to you as an observer. It's not easy. Experimenter bias needs to be incorporated into Bayesian inference. Suyag, whoever he is, gave a poster a while back showing how you could do this, how you can introduce bias into inference. He has used an ESP example as just one trivial kind of example. Enormous statistical evidence has been collected showing the evidence of ESP. But scientists disbelieve anyway, because they assume experimenter bias and error is a better explanation of the results. Suyag has shown how this bias can be quantified, albeit subjectively, altering the posterior probabilities to align better with scientific judgment rather than statistical analysis. Okay, so none of what I've been saying provides a justification for bad practice of science. There are plenty of unjustifiable factors that lead to the publication of non-reproducible results, as many people have pointed out. An incentive structure that requires many publications for career advancement or that provides monetary rewards for particular results. You heard a lot about that in the drug industry. A bias to publish positive results, results the researcher prefers, or results that confirm the researcher's beliefs. A bias, usually unconscious, to design studies and analyze results in a way that confirms one's beliefs or preferences. The tendency to find as more important and interesting results that are novel by virtue of being unlikely. The otherwise praiseworthy motivation to report results that have the potential to help society. That a factor that plays a big role in health research. And a motivation which isn't quite as praiseworthy to report results that have the potential for translation into profits. The increasing tendency for journals to publish short reports, especially ones with unlikely findings that are therefore newsworthy. Now, it seems obvious that remedies to current practice of science should be aimed at such sources of error and invalidity. But that's a lot harder to implement than one might imagine, because the remedies that are proposed often do more harm than good. Just an example is a change in the incentive structure. I even once participated in a science editorial. Oh.
15 minutes for questions. So.
Well, let me just do this one. So the current incentive structure tends to reward publishing many articles. That's especially important for young scientists hoping to get jobs. These incentives tend to cause publishing at early stages of investigation and at stages prior to additional studies that might better confirm validity of findings. And many journals prefer short reports that facilitate the tendency to publish before validity is well established. So I even at one point joined in a proposal that the incentive structure be changed. For example, judging a scientist by a small number of best publications rather than some assessment that uses total output. But there's problems with this remedy that I sort of also came to realize. Of course, first, an expert reviewer, and you need expert reviewers, almost always know a scientist's total output. It's hard to ignore that information, even if you're told to only evaluate the best publications. And perhaps even more important, productivity is a desirable characteristic in any profession, including science. It reflects motivation, writing ability, and a number of other desirable traits. Thus, productivity level probably should not be ignored when we're assessing scientists. So it's a very difficult issue about simply changing the incentive structure, because it has some costs as well as benefits. Okay, since I'm out of time, this could go on for a while, but I'll just stop here so we can have questions. Thanks.
I have two little remarks. One from the beginning about the publication of not having all these standards and being more loose about the publications. That was a major feature of toward the end of the 19th century and across into the beginning of the 20th century, when Germany was the source of the best scientific work going on. That was a major feature of their research environment, was that they would publish, they instead of just publishing a few things, they were quite loose on which things they published, and that may have been a factor. A number of people claimed it was at the time. So that's one. And the second one on judging somebody for promotion and stuff by just picking out a few, a couple of major publications. I was on the promotion and tenure committees of about 5 different departments here. And one of the things about economics was that getting a journal, they had, I think, Econometrica, getting a publication in Econometrica and that had people say that was worth, like they didn't count publications. They would look at one publication in that journal, that'd be enough to get you tenure. And it was by the way, different departments had enormously different standards. It was amazing how different, they all were. But that was one example of one that was quite different. And it was more like what you were saying.
Okay. So thank you for taking the time to reflect on your thoughts about the reproducibility crisis in science. But I think, so to take a step back from and look at what you've said in general, to me it sounds like the general narrative that you put forward looks something like a focus on reproducibility has spawned a bunch of proposals and strategies for improving science, but for each of them you've suggested, don't worry guys, we, the good scientists, already engage in practices that will address these concerns in the long run. And so the rhetorical take of this argumentative strategy against reproducibility is that science is fine. But that's just not true. You hand-wavily mentioned the autism study, and that caused immeasurable harms. We shouldn't let these kinds of things get through. We talked about corporate bias yesterday, which is one of many things that are pushing against scientists' abilities to make good judgments. There's also the fact that domains in which replication is a focus are domains where methods aren't carefully tested or thought about, which is what Jackie was talking about. And so things like exact replication are not about advancing theories. They're about making sure we know what we're looking at. These are barriers to scientific progress, and proposals for pre-registration or transparency, sharing code, data, changing journal practices. They're concrete proposals that scientists have put forward to address what they've identified as issues in their practices. And saying we're fine is attacking the rhetoric of reproducibility without looking at the underlying issues. And so my biggest concern is that this strategy of attacking the rhetoric is just entrenching the kinds of scientific hubris that have got us here in the first place.
I didn't expect that my proposals would be completely accepted, especially in a conference on reproducibility. I would say that in sort of response to this issue, of course there's problems. It's just that the problems aren't easy to solve. And the question is whether we can introduce something like one-size-fits-all remedies that are going to help us do better rather than make us do worse. Some of the remedies, I think, would actually slow progress. Now, there's some things that are difficult to handle. Who's going to be able to figure out a way to stop fraud? We don't know how to do that. I mean, come on. But these are rare cases in science. They make a lot of publicity when they're found, of course. They make news. But these are very rare cases. Most scientists are interested in truth and knowledge and not in simply producing results through fraud. So that's a difficult example. Then we have cases where people are doing things wrong because they're in pursuit of profits. Well, that's sort of true of all of human society. And it's not going to be easy to stop that. We can think of possible remedies to try to help the matters, but we have to be careful not to introduce remedies that attempt to solve these problems that are going to do more harm than do good. And it's not easy to find solutions that do that. I think that there's sort of a legal approach to how we do science that says, let's protect against the worst possible case. Well, you can do that. Well, you can try to do that. But sometimes that just introduces all sorts of regulations that harm people in general, or scientists in general, rather than promote progress. So we have to find a balance. And what I'm really saying is I'm trying to say we need to have a balanced approach to these problems. And most of the focus in recent years has been on problems and remedies for these problems, and has failed to look at the successes of science and what works well. We need a balanced view of these things, and right now we're way out of balance. That's the main point of trying to make. So I'm not really claiming there aren't problems and that need to be addressed. In fact, I said so earlier, but I think that we're way out of balance at the moment.
Yes, a brief. Of course, at the level of generality at which you discuss that, I think it's hard to disagree because it's all in general. Nobody is against progress, and nobody is against good science. So the problem are not at that general level, but at the fact that, for example, as you said at the beginning, there's a lot of average or bad science. We don't care because we won't cite it, and the good scientists will know how to see that. The problem is that the money, most of the money that the libertarian scientist wants to say, leave us alone, we're good enough, we're doing, which I'm sympathetic to that, because as we're doing science, we're happy in our small universe, but we tend to forget that we don't do that with our own pocket money. We do that with public money. And I think it's part of the reason why people say, well, if we agree that over the last 30 years, there's been a change in this structure and there's more and more bizarre thing going on, it means that the resource allocation is not optimal. And so is it possible that this libertarian view that let the scientists do it alone will make an optimal distribution of the limited amount of money? Because we know that there's never enough. We want to double NSF again. I'm not against it. Just that, well, in US, I think there's a big, large deficit that they will have at some point to look at. So there is this. But I will just conclude with one thing which is behind and again, I don't disagree with this, I think, is that you said that the aim of science is progress. And from that, you say, okay, if we do this, it will harm progress. Okay, but I don't think the aim of science is progress. The aim of science is establishing valid knowledge. When Aristotle do biology, he doesn't want to make progress. He wants to add valid knowledge. Of course, the consequence of science having to establish valid knowledge, the consequence will be there will be some progress. More if we have more money, less if we have less. If you look at the Middle Ages, there were great advances in logic with very few money, but it was not rapid progress. It was accumulation. So the aim of science is not at all progress. The consequence of the aim of science can be progress, but if you start that the aim of science is progress, you miss something fundamental. Science is about valid knowledge. And so the libertarian view is nice, but it forgets that taxpayers put limits on your libertarian view of science.
Well, I don't want to get in debate about the meanings of words. I define progress to include the accumulation of knowledge, of course, and advancement of knowledge and truth and so on as we get better and better at approximating whatever the underlying reality is. That's what I define as part of progress. So otherwise, we'd be debating about the meanings of words, and that's not useful. The question of funding is an important one that I didn't address. And there are all kinds of problems in trying to find the right way to fund science. These are political issues as well as sort of substantive issues about the nature of science. There are incredible problems of how science gets funded and the way it does. And many of the problems are due to the fact that the criteria for what should be funded is very inadequate at times. And in particular, the people reviewing the proposals are often not adequate to do the job. I once proposed to the head of NIH in one meeting that no scientist should get a grant unless they promise to serve on a grant panel if asked.
Yeah,
that seemed like a good idea to make sure that the best scientists who are getting funded would serve on grant panels if they were asked to do so we'd get better reviewing. That was sort of thought to be a good idea at the time, but of course nothing came of it. But there are all kinds of problems with the way we fund science, and part of it is political, and just in different countries have stress in terms of the amount of funding they have available. And there's also problems about the funding of basic science versus translational science or applied science. There's been moves over the years to move away from funding basic science where the long-run discoveries take place, and there's been a move toward trying to fund things that will produce progress and results in the next year. That's not too good an idea, but it's politically saleable, and that's why this is going on all the time. So even NSF in the United States, which is supposed to fund basic science, has been moving toward translational science more and more. I don't think this is a good idea, but this is the way life is, because we're all driven by politics. Anyway, there's all kinds of questions like that. So I agree with that. But that's a little bit aside from the reproducibility issue, except for the fact that the focus on reproducibility is harming funding for science already. So that's an issue too.
I apologize because there are multiple
you have a question at the back over there.
Yes. I apologize, there are multiple people in the queue. We only have a minute.
Okay.
So there's time
I didn't
one
know you
question.
could see that.
And I think Chris, you
Okay.
next. Yeah, and we are going to have a lunch, so we can talk to Richard then. That's okay.
So I don't know all of the literature about pre-registration in detail, but I feel like there were some motivations that were missing. So the way it's implemented might have the sort of, work for lawyers implications that were mentioned earlier, or the kind of constraints that you're worrying about. But there are two things that seem to be missing from the discussion that seem to be crucial. One is, are there certain types of research that are more appropriate for having pre-registration, as opposed to exploratory research or research where the experimental design is open-ended? And at least in physics, the kinds of blind data analysis that Alan was mentioning earlier are often motivated by the well-known foibles that we all have in doing statistical analyses, and the kinds of things you mentioned about stopping at appropriate points to maximize the evidence that you've collected. And so there do seem to be good motivations for having some constraints on the way you're analyzing data to counter failures that we recognize we often make. Now that might be generalized in the way that pre-registration is talked about in different fields, so that it becomes something less plausible.
I don't think, okay, I don't think it's a, I don't think it's a field issue. In other talks, I pointed out that there are good cases where pre-registration is a good idea, where the result that you're trying to affirm or deny, let's say, is one that has immediate practical, societal, or health implications. So if you are deciding, if you're trying to propose immunizing millions of people on the basis of some reported result that you want to check, you obviously want to carry out perhaps costly and time-consuming research to check that very carefully. And that means that you ought to work out the best possible design in advance that you can imagine, so that you do it well as possible, because it has immediate, practical, important implications for what's going to happen. You don't want to do it wrong. So there are clearly cases, and these would be less exploratory science and more applied science or application science, translational science, where you would want to at least be as careful as possible in carrying out the research properly, much more so than in other domains because of the immediate practical importance. So there are cases like that.
All right, well, let's thank our speaker.